Dear students, in this video we are going to learn about the concept of priority inversion in operating system. Generally, a solution to the critical section problem must hold the three properties. One is mutual exclusion, another one is a progress, third one is a bounded waiting. What is mutual exclusion? If one process is executing in the critical section, no other process can be in their critical section. So that is mutual exclusion. What is progress? If no process is executing in the critical section and there exists one process that wants to enter into the critical section, then the selection of the process should not be postponed and it should be immediately granted permission for entering into the critical section. That is the meaning of progress. Bounded waiting says that a bound must exist on the number of times that other processes are allowed to enter into their critical sections after a process has made a request to enter into the critical section. So that means a process has requested for entering into the critical section. But before it is permitted to enter into the critical section, there must be a bound that must exist that how many number of other processes can enter into the critical section before the permission for this requested process can be granted. So that means every process must wait in a bounded amount of time for getting permission to enter into the critical section. A process should not be made to wait unbounded amount of time for entering into the critical section. So these are all the three conditions that needs to be fulfilled by any solution to the critical section problem. Priority inversion is nothing but it is a bug that occurs when high priority process is indirectly preempted by a low priority process. So generally, what is the priority scheduling? When a high priority process wants to enter into the critical section, then a low priority process may be preempted, and then a high priority process can continue its execution. But here in priority inversion, the high priority process is indirectly preempted by a low priority process. So that type of situation exists. Then that is called as priority inversion. So why this scenario exists means the low priority process is holding the lock and the higher priority process do not have the lock for accessing to that particular resource. So therefore, the high priority process need to wait for the process to continue its execution. Priority inversions are two types: bounded priority inversion, unbounded priority inversion. Bounded priority inversion. In the simple case, high priority task would be blocked as long as the low priority task held the lock. This is known as bounded priority inversion. That means high priority task will be blocked as long as low priority task hold the lock. The length of the time of inversion is bounded by the amount of time the low priority process is in the critical section. Now let us examine this diagram. So there are two processes. One is task L, another process is task H. The low priority process L is in its normal execution and it has the lock on a particular resource and it enters into the critical section. So task L is now in the critical section. It is executing. L is in the critical section. At this point of time, task H wants to execute. So task H will go for its normal execution by preempting the task L. And task H requires the lock on a resource, but this lock is held by task L. So therefore, the task H fails to acquire the lock on the resource which is held by L. So what happens? Task H will go to a waiting state and then it will let the task L to enter into the critical section and complete its rest of the critical section execution. So this is called as bounded priority inversion. That means task H is made to wait for the completion of the low priority task L. Once the task L completes its execution, it releases the lock on the resource which is required by task H. Then task H acquires the lock of that particular resource, then enter into the critical section. Then after completing the critical section, it releases the lock, then it will enter for the normal execution of the task. In this way, certain amount of time, the task H is made to wait by the low priority task. So this is called as bounded priority inversion. Because both the task H and task L require the same resource lock. So that is the reason task H is made to wait for the release of the lock by task L. So this is another diagrammatic representation of the bounded priority inversion. Task L is now executing. Normal execution is completed. Task L wants to continue in the critical section. It is holding the lock for the resource. So therefore, task L enter into the critical section. Now the high priority task H is coming and H is trying to enter into the critical section. So it will preempt the task L. But when H try to acquire the lock for the resource, then it fails because the lock of the resource is held by the task L. So therefore, H fails to acquire the lock. So therefore, it is entered into the waiting state and task L will continue its critical section execution. Then after completion, it releases the lock. Then once the lock is released, then the task H will be acquiring the mutex lock on that resource. Then task H will continue its execution in the critical section. Once task completes its execution in the critical section, then it releases the lock on that resource. Then task H will continue its normal execution. So once the normal execution of the task H is completed, then whatever execution is pending for the task L, it will continue until that the task L is in the blocked state, waiting for the high priority process to complete. So in this way, in this period of time, the task L is completing its execution in the critical section because task L is holding the mutex lock on the resource. So therefore, the high priority process H is made wait until the release of the lock by the low priority process. This is bounded priority inversion. Coming to unbounded priority inversion, this occurs when a medium priority process interrupts H while it holds the lock. So consider a scenario. There are three processes: low priority process L, high priority process H, and medium priority process M. So as usual, the low priority process is in its critical section because it holds the mutex lock on the resource. So it will continue its execution in the critical section. Now, high priority process wants to enter into the critical section, but it fails to acquire the mutex lock on the resource because it is held by task L. So then what happens? Task H will be entering into a waiting state. So during this process, what happens? The process L will continue its execution in the critical section. During its execution in the critical section, a task with priority M which is greater than the priority of the task L is or wanted to perform its execution. Then what happens? The task M will preempt the task L because the priority of the task M is greater than task L. So therefore, the task L is preempted and the task M will continue its execution. That time, already the priority high priority process H is already in the waiting state, but the process M, whose priority is lesser than the priority of the H, is entering into the execution state. So therefore, this is making the unbounded waiting time for the high priority process to any amount of time. Once the task M completes its execution, then the task L will complete its execution in the critical section because it is holding the lock. Then it releases the mutex lock on the resource. Then high priority process will acquire the lock on that resource. Then it will enter into the critical section. It completes its execution. Then high priority process will go for normal execution, and finally it finishes its execution. Then whatever rest of the execution pending for low priority process, that will continue and it will finish. In this way, task M is indirectly preempting the task H from being entering into the critical section. This is called as unbounded priority inversion. So let us see the another diagrammatic representation of unbounded priority inversion. There are three tasks L, M and H. The priority of L is 1, priority of M is 2, priority of H is 3. The initially task L is in its execution and it wants to enter into the critical section. It is holding the mutex lock, so therefore L will enter into the critical section. That time task H comes. Task H wants to enter into the critical section. Then it fails to acquire the lock on the resource. So therefore, task H will not be permitted to enter into the critical section. So it will be in the blocked state. So the task L will continue its execution in the critical section. It releases the lock. Task L will continue its execution. By the time it is continuing its execution, the task M will come for execution and this task M will preempt task L because the priority of M is greater than the priority of the task L. Then task M will go for execution and it completes its execution. Then during that time, task H is already in the waiting state. This makes an unbounded waiting of the task H. Then task M after completion, then task L will continue its execution because it is holding the lock. After completion of the execution in the critical section, task L releases the lock. Then task H will go for execution in the critical section. Then task H completes the normal execution. Then whatever rest of the execution pending for L is there, it will complete after the task H is completed. So here task M is indirectly blocking the task H for certain duration of the time. This duration of the time may be unbounded by task M. As long as the task M wants to execute, it will execute and make the process H waiting for an unbounded amount of time. So this is called as unbounded priority inversion. This leads to serious problem because the high priority process should never be made wait for unbounded amount of time. So we need to provide solution for this type of unbounded priority inversion. There are two protocols that provide the solution. One is priority ceiling protocol. Another one is priority inheritance protocol. In priority ceiling protocol, each of the resources in the system is assigned a priority ceiling. So the assigned priority ceiling is determined by the highest priority among all the jobs which may acquire the resource. For example, there are three processes that access the particular resource or the priority of the three processes are maybe 1, 3, 4. Assume 1, 3, 4. So the resource R is required by all the three processes whose priorities are 1, 3, 4 respectively. Now the priority of this resource is made as 4 because the highest priority of the process is 4. So therefore the priority ceiling is assigned to this resource. The assigned priority is determined by the highest priority among all the jobs. So whenever a task works with a particular resource, it takes the priority of that particular resource and the task priority is boosted to the priority ceiling associated to that particular resource. In that way, even a low priority process acquires the lock on the resource R. The low priority process priority will be boosted to the priority of the. In that way, the priority of the process will be boosted for certain duration of the time and the execution of the process in that priority level only. The priority inheritance protocol. Boosting the priority of the process, holding the lock to that of the other process that tries to take the lock. Now let us see the priority ceiling protocol. Task L and task H both wants to share the same resource. So the priority of the task L and task H are 1 and 3 respectively. The priority of the H is more than L. So therefore, whatever resource that the priority, the L process and H process needs, the priority of this resource will be made as 3. So therefore, when a process L acquires the lock onto the resource R and wants to execute in the critical section, then immediately the priority of the task L will be boosted to the priority of the resource, that is 3. So this is equivalent to the priority of the task H. So now the task L will complete its execution with the priority 3 instead of 1. So therefore, during the execution of the task L in its critical section, if any other process like M come and wants to execute, then the task priority for M is lesser than the task priority of L. So therefore what happens? The task M will be made to enter into a blocking state. So then task L completes its execution and it releases the lock, and the task H will acquire the lock for that resource and it will complete its normal execution as well as the critical section execution. Then task H will complete its execution. Then task M will go for execution. In the meantime, if again task H wants to execute its pending task, then task M will be preempted and task H will be continued its execution, and once task H completes its execution, then task M will continue its execution. Then once task M completes its execution, then if any pending task for L is there, then task L will go for its execution. So in that way, priority ceiling protocol helps in making a higher priority process to complete its task before a low priority process. Priority inheritance. Priority inheritance is nothing but boosting the priority of the process holding the lock to that of the any other process that tries to take the lock. That means here L is one process, H is another process. Both processes wants to share the same resource R. Then initially L is holding the lock on R. After some time H requests for the lock, but the lock is not held by L. Then what happens? The process L will continue its execution. but the priority of this L will be boosted to the level of the priority of the H, because the L process will complete its execution before the process H, because the process L is holding the lock on R. So therefore H is made to wait until L is completed. In order to eliminate unbounded waiting for the H, the priority of the L is boosted to that of the priority of the H. In that way, the process L will be executing its operation in the critical section with the priority of H. So therefore, in the middle, if any another process like M request for the CPU access, then the process M will be made to wait, because the priority of L is equivalent to the priority of the H. So therefore M will not terminate the process L. So therefore M will not preempt the process L. So in that way, priority inheritance protocol will help the higher priority process for not entering into an unbounded waiting condition. Now let us look into the priority inheritance. Task L is initially executing. It is completed its normal execution. Then it acquires the lock of the variable. Then it enters into the critical section. When it is in the critical section, a high priority process comes. Task H completes its normal execution. Now task H wants the resource R, but the mutex lock of the resource R is held by L. So R cannot enter into the critical section. So then therefore what happens? Task L will be permitted to continue its execution in the critical section, but the priority of L will be boosted from 1 to that of the priority of the H. That means now the priority of the H, L is equivalent to the priority of the H. So therefore task L will be executing with high priority, that is 3 instead of 1. Then once the task L is completed its execution, it releases the lock on R. Then task H will continue its execution in critical section by acquiring the lock on the resource R. Once task H completes, the lock on resource R is released. Then task H will complete its execution in the normal section. Once the normal execution is completed, then any other process which are waiting for CPU, for example, task M is needed CPU for its execution. So then priority of M is greater than priority of L. So therefore M will be continuing its execution. During the execution of M, again H wants some more time for its completion. So M is preempted and H will continue its execution. Once H is completed its execution, M will continue its rest of the execution. Once M completes its rest of the execution, L will continue its pending execution and finally terminates. In this way, priority inheritance will facilitate all the processes to execute one after the another without any unbounded waiting condition to encounter. Thank you for watching this video.